All right, here we go. Hello, everyone. Hey, Bill. Um, starting to get the exams back in. I will have a summary of everyone's grades, where they stand, emailed to you individually as I get them in on my paper, my Excel spreadsheet of grades. Um, and then update where everyone's at. I'll factor in the homework grade. If you have had any problems with the exam, taking it, being disconnected offline, timing issues, email me and let me know what's up. There's a couple people there where the scores are lower than what you did on paper, and I'm not sure if it was the format or you waited too long and timed out or something. I'm going through them individually because I can see the answers you typed in. I'm seeing if there were things where it was an obvious like sign error or misreading a table or such, which I can do, and give partial credit where possible. So please just let me know what's going on. I'm going to put that all in the emails going out tonight. And remember, homework, it has no technical due date. Go back, finish all the homeworks, and that will really help boost your scores. Today, we're going to talk about two more types of confidence intervals. We're going to look at the confidence interval when you don't know the standard deviation of the population. And that uses a whole new distribution that we're going to look at, which I think, what was it, Gossett? William S. Gossett did that. He worked for the Guinness Company, and it was one of the kind of first examples of statistics used in marketing in the 1800s. And he published a paper on this idea of when you don't know what a population's standard deviation is, how you can infer it with this new type of distribution, which we're going to call a T distribution. So we're going to have T scores versus our Z scores. Another reason why I use the English is Z over Z. Oh, what's your Z score? What's your T score? There's a rhyming similarity to that. But if I clearly say Z score and Z critical values, you know I'm looking at the normal. But if I say T score, I want some T with that. We're looking at the T distribution. It's called the student's distribution because Gossett worked for Guinness, and this was considered to be trade secrets of the company. Um, he wrote it under a pseudonym called Student, and so the paper was published, and it was Student's T score. And so we're going to look at T scores. The process is not that different from finding the critical Z scores and the confidence interval. Just the distribution that we draw data from is different. Draw our area under the curve is different. And the T score is kind of interesting because it is if I had an infinite amount of samples, it would become a normal distribution. So the equations for it actually build the normal distribution, but what the T score and the student's distribution allows us to do is actually go, well, I only know 10 people. I only know 100 people. I only know a certain amount. Can it be used for stocks? Yeah, all these things can be used for stocks. To be honest, the problem I would say with stocks, and what we're doing right now, is we're talking about things with one variable, one mean, and stocks are a multivariate things. And these equations and things we do can exist in a multiple parameter space for many, many variables. We're learning the one variable version of it, but when you look at the interaction of stocks, you would want to take into account different variables. So, for example, I'll use IBM and Apple. Though this isn't as truly clearly correlated, the value of IBM stock is related somehow to the value of Apple stock, but not directly. And so you have to figure the relationship of how one influences the other. And when you lay all the different variables of all the different stocks down, you can get this complicated, multi-dimensional graph that describes things. Then you can also take external economic pressures and put those variables in. And you end up looking, I have a friend who works in this, he was also an astronomer, and he works at this in Chicago, with a hedge fund doing predictive analysis of markets, and they look at 50, 60 variables at once and how they work out. The concept is the same. The concept is the same, and what you end up doing is your variable of interest, the stock in value you want, or the market value, be it like the whole Dow, or an individual stock in it, or a collection stocks in it. You look at all of the variables influencing it, and then you project the one value you're looking at back into a normal or a plot so that you can look at the one value you want. I'll actually do this on the blackboard really quick here. Get goofy faced caricature out. And so what ends up happening is the real world graph, I'll just make it, ends up being some surface of many things, and you'll have bumps and ridges that are three-dimensional, kind of looking like stalactites and stalagmites, and each value in x, y kind of represents a variable, and you'll hone in, and let's say that's Apple stock there along this axis, and Apple stock correlated to some other backgrounds. And what you'll do is you'll take this little peak in stalagmite in your big ripple that comes across, and you'll go, hey, these are the values I have of interest, and you'll flatten that into a normal curve around those values. So everything flattens down back into what we're doing. And you can get a lot of equations that flatten these back down to this. But we have to start with the one variable so we can build up to the multiple variables. And I'm not going to force you through multivariable statistics here. A lot of people never touch that unless they go into very high-end economics or scientific statistical, because we can get these equations that flatten them down for day-to-day use. Sorry, that was a nice little digress there, Bill. All right, so the student's T statistic we're going to look at, and so this T distribution and a T distribution table. That's going to let us reinterpret the idea of confidence intervals for a population where we don't know the spread of the population. All we see are our samples, the experiments we run, our surveys we take, the polls that we're releasing. That's the only information that we're getting back from this. And so we want to take that information and give as much as we can about the population. The best I can say is this is what happens when you don't know anything about the population at all. You just have your experimental data, and you're going to build this, and you're going to build it towards something that looks normal, the normal distribution. You kind of know in the background that this is a normal thing, but you don't know how the large population is spread out. And so you're going to make your measurements and you're going to build it up. So in general, the idea of doing everything we exactly did, if we knew the confidence interval, or if we knew the population standard deviation, we can do the same process. So we're actually going to start with the idea of what is the margin of error. And we're going to look at that margin of error in our new system. We're going to work our way to a margin of error. What we want to do is we want to talk about the t-score. And so if we have a random variable and it's approximately normal, then the t-score is going to look like this. Let me put it here. So when the population standard deviation is unknown and the sample size is less than 30. Wow. Sorry, I have my headphones on and I've got two microphones here and I've kind of been pacing back and forth. I really do like standing. I feel a little more energetic, but I've noticed there's certain places I stand and point that I try to have the microphones cover most of the space where I'm at. And I just hit a sweet spot there. I noticed my voice went up when I turned my head a little bit there. So sorry about that. I'll try to balance that out. I have like my effects units for my guitars over there. I'm thinking of running the compressor through to limit the volume and compress all this. But that's this weekend. Every weekend I'll observe something new. Try something new and try to tweak out the rough edges. So what we do is for sample sizes less than 30 and the random variable is approximately normally distributed, we have a t-distribution. And so this really nasty equation here for this t-distribution, which is the sample average minus the population average divided by the sample standard deviation divided by the square root of n, or the number of things that we have here. Now, the sample population, we have to remember if we go back, or the sample standard deviation, if we go back to our front matter here, but I'll just write it up on the blackboard bit here, is this variable s, which is the standard deviation of the sample, is the square root of each data point minus the average of each sample squared over n minus 1. And I said this n minus 1 thing would come back, and it's going to start coming back here. When we did this in chapter 2, the difference between the population standard deviation, which I'll write this down here, was each variable minus mu squared over n. And the reason this happens is the sample doesn't have the whole population. And so we have to take the 1 off of it. We're not seeing everything. And that actually now comes back to hit us here, because this is happening underneath this here that we have here. So this s here has a square root of n minus 1 underneath it. And so this makes up what we're going to call a t-value. It's really, really close to a z-score. Let's compare this to a z-score. So z was x minus mu, x average minus mu, over, and we took this one over, was it the standard deviation of the mean, right? I think. I want to just go back 2 pages. Make sure my z-score was... which was the standard deviation of the mean. Where's my ZC? Well, I'm seeing my error interval, which was the last thing in my notes. As I flip through my notes here, interval, confidence level. Where is my z-score? Constructing the confidence interval. Oh. So what happens when you move your notes into a new chapter and you pull up or new section, you go to pull up your old one and they're out of order because you were talking through them. Yeah. Z x bar. And S is going to be x minus, x bar minus mu. Not S. T. It's going to be x bar minus mu. So it keeps the same upstairs. Now I got to move these papers because this is not in a good place to write. T is x bar minus mu over S divided by square root of n. Now remember, this here is x bar minus mu over the standard deviation divided by square root of n. So these are similar constructions. We just called this standard deviation divided by square root of n the standard error of the mean. So the t-score has the same form as the z-score. The difference is we're using the sample's standard deviation. Why are we using the sample's standard deviation? We don't know the populations. So we have to use what we can measure. And so we have to use this because we can measure that. And this is the part where, as I tried to warn through statistics, the equations start looking the same. They're very similar with an n-1 here. You'll see eventually there's an n-2, but they have the same form. And I am going to try to emphasize that same form means we're talking about a similar thing, but in a different context. So we had our z-score is x bar minus mu divided by the standard deviation of the mean. Right, and that's in our front matter of the book. The t-score is x bar minus mu divided by the sample standard deviation divided by square root n. So the difference in variables tells us what the difference in our context was. And back in the beginning I said, when we are doing things with the population, we use Greek letters. When we are doing things with the samples, we use the English letters. And here, everything is using the English letters except the mu. And the sample average, the averages of the samples, and mu are the same. All right, we go back to the previous section. The average of the averages. If I average all my samples together, we are going to say that is the best estimate of the population mean. So mu is something we can never get rid of now because any estimate we use underneath it is the best approximation of the population mean. But we don't know the population standard deviation. We can't use sigma. So our equation can't use sigma. And that's where the t-table comes in. And that's how I remember the difference between the z-table and the t-table is, do I know the population standard deviation? Nope. Okay, I have to use t-tables. And so what do t-tables look like or do for us? So, the mean, median, and mode of the t-distribution are equal to 0. It's the same as a normal distribution. It's going to be symmetric about that. It's bell-shaped and symmetric about the mean. The total area under the curve is 1. This is the same as our normal distribution. But the tails are thicker. It doesn't chomp down towards 0 as quickly as the normal. And the standard deviation of the t-distribution varies with your sample size. The more samples you have, the closer the standard deviation gets to 1. But on a t-table, it's greater than 1. It's a little bit wider. That's what makes the tails fatter. And so this is the secret sauce here. We've created something that's just like the normal curve, almost. And we let the standard deviation change depending on how many samples we have. So I want to go right to the graph here. And I'll go back a slide on this. But if we look at the graph here, we're going to call these things called degrees of freedom. And for 30 or more degrees of freedom, the t-distribution is close to the standard normal. Notice when we were doing the central limit theorem, we said if we have 30 or more things, we can assume, we can make this assumption. We don't need to know that it's normally distributed, because if we have 30 or more things, it's going to approach it. Well, here that 30 or more comes into. It's a limiting factor. It has to do with the natural logarithm, or not the base of the natural logarithm e, and how that approaches for large n values. These things start approaching each other. But look at the shape. This shape looks very close to the standard normal curve, which is in blue. thicker tails. I hope you can see my pointer here. Let me make sure my pointer's moving. No, the pointer, yep, there's, okay. There, we got the pointer back again. All right. So, there is your standard normal curve. Here I have 5 degrees of freedom, and I'll define degrees of freedom. They relate to the sample number. Here I have 2. So notice the larger the degree of freedom is, the closer this curve comes to the standard normal. Now, because the area has to add up to 1, these all have different heights. The standard normal curve has more things about the mean than the t-curves do. See my t-curves here? The larger my degree of freedom value is, the higher the part is in the mean. And I'm hoping my arrows are pointing, yeah. And I always get worried about how these arrows work. All right, so what I want to do is I want to go back and define degrees of freedom for you, but I wanted to visually look at this. Of course, it's the slide that dies. Why does that do that? Let me look here. Huh. There we go. For some reason, certain slides are doubling each other periodically. I will work on fixing it, but at least I fixed it for that one. All right, so the t-distribution is a family of curves. There is a parameter that changes from it, and this is going to be called the degrees of freedom. And this is a name that came from mechanics. For every possible value that you have for an axis, it's called a degree of freedom. And what happens here is each piece of data you have can help determine the different values that could take on place here. If I have one piece of data, I'm not going to have a standard deviation or a spread. Everything is about the one piece of data. So there are no degrees of freedom. Everything is specified by the one piece of data. If I have 2 variables or 2 pieces of data, I have one more degree of freedom. And if I have 0 with 1, I have 1 with 2. And so for every piece of data that I put down, I gain a degree of freedom. It means that I have a choice to make. Am I starting with the first sample and comparing it to the second? Or am I starting with the second sample and comparing it to the first? And so this choice of how each piece of data falls down and comes together determines the degree of freedom. One piece of data has no degrees of freedom. 2 pieces of data has 1 degree of freedom. 3 pieces of data has 2 degrees of freedom. And so our degrees of freedom equation comes out to be whatever the number of samples we have taken, which is our little n, minus 1. So if I take 18 samples, my degree of freedom is 17. If I take 20 samples, my degrees of freedom are 19. I have 1 less degree of freedom than my samples, the number of samples that I have. And so if we come back to here, this black line that I'm following with 2 degrees of freedom represents 3 samples, or n equals 3. This black grayer line with 5 degrees of freedom is the distribution from 6 samples. Now, and the normal distribution is the distribution with an infinite amount of samples. So what has happened was someone went through, calculated everything you needed for the normal curve that would work if you were doing, your mean median mode is 0, your standard deviation is 1. And then someone went through and said, okay, well, we're going to take this degree of freedom parameter, and that's going to change our standard deviation. And then they went through and they calculated for every value possible, and they built tables for them so that you wouldn't have to do the calculation. And so here's an example of a 95% confidence when the sample size is 15. And there's a table. So in the book on page 311 is the table. Let me check the front matter. The t-table should be in the front matter here. Sorry, my mouse clicks here. I'm going to get another mouse pad. Or at least I have a mouse pad somewhere. I've been using the laptop so often that I haven't pulled that out in a while. Yeah. So over here, let me put you up onto the browser. If we look at the front matter in the textbook, table 5, that's the fold out in the textbook that I let you have for exams, which is also up on the web page for the people that didn't have the fold out. Here is what is a T distribution or a T table. Now online there are T tables that give a larger level of confidence. Right, the level of confidence is C, and so we have an 80% confidence, a 90, a 95, a 98, and 99. I have a older statistics book that does this in it's like 5 pages, and I think it starts at around 80, and it does 1% for each. So you have 80, 81, 82, 83, 84, 85, and so on, working up. And they pre-calculate the volume or the values. But notice there are 3 columns up here. This table is going to get used in different ways, very similar to how we use our Z table. And so when we're doing a confidence interval right here, we're looking for the area in the curve between 2 t-scores, which is what we're talking about, is a confidence interval. So the shaded area is the level of confidence. And so we're looking at the value up here. Later on, when we do hypothesis testing, we're going to look at the tails. And the tails are these things called alpha here. Well, notice that the tail is related to this graph. This negative t-score is related to this graph. And so we have a 1 and a 2 tail. Right? Is it a right test? Is it a left test? And so we have this graph here that tells us, hey, you want to look up these values, you only need to look up the values here, depending on what you are testing. Because we are looking at a confidence interval between a negative t critical and a positive t critical, exactly like we did with the z-scores, but a different table, we're looking at this graph. We'll learn these other ones as we go through. And so that's the level of confidence. And so we pick our level of confidence, and then we look for our degrees of freedom. So you could think of the degrees of freedom, that's 2 samples, that's 3 samples, that's 4 samples, and so on, that there's an additional sample to all of these. But because the mathematics of it, this is the parameter you're using, everyone talks in degrees of freedom. And so you look down here for the degrees of freedom you have, and you come down to your confidence level, and you're going to get your t-score. So let's go back, and here's the example. So I have 95% confidence, so that's a 0.95 confidence level, and I have 15 samples. Well, 15 samples is 14 degrees of freedom, because your degrees of freedom are always 1 less than your samples. So I go to my level of confidence, and I find 0.95, and I go down the table until I get to 14 degrees of freedom, and there's my t-score. So the process is the same as what we did with z-scores. The table is different. And that different table is in the fold out of the tables. Again, once we get around 30 samples, the T table is so close to the normal table that we talk about the normal score. And remember, when we did the central limit theorem, that was our boundary point, right? You needed at least 30 samples to use the central limit theorem, unless you knew the thing generating your population was normally distributed, which is an okay assumption, but here now we can be specific. We can let our data tell us things about the population. We can operate with no knowledge of the population at all now. No assumptions. That's the power of the T tables. That's the power of Guinness beer. Right? Because Gossett worked for Guinness beer. Right? It's funny. I had a student in the past that got me, after they had graduated, a Guinness sign. But when I was a kid, in my 22, 23, I used to collect Guinness posters because I was never a big fan of American beer, and this was before the microbrewery resurgence or surgence or whatever the craft beer is, and I didn't like beer until someone got me a Guinness, and I had a thick stout Guinness, and so I collected Guinness posters from bars. Because they had this Guinness is known for having one of the first advertising campaigns, in the mid 1800s to late 1800s. It was extremely successful, and then all the way through World War I and World War II, they had like a "My Goodness, My Guinness" set of posters, and I collected the "My Goodness, My Guinness" posters. I think they're still in my parents' basement, but I mentioned this, and so a student had gotten me like a Guinness display out here about how Guinness works with statistics. But think about what people's love for beer did, and wanting to sell this Irish stout beer did. Created a mathematical framework where you don't need to know anything about a population. You just need to take surveys and samples, and you can now start giving information about the population within a confidence level. The mathematics work that we get a confidence level that isn't the normal distribution. It takes into account how much you know. The degrees of freedom take into account how much you know, and your confidence interval says how sure you want to be of the result. It's a very powerful tool set. Where's Benjamin Franklin quote? I don't know if it's proper, and it's come through, right? How do we know that God loves us? Beer is how we know God loves us. Beer has been through history. We found Egyptian beer recipes. Beer seemed to be beer and yeast went side by side. So baking yeast and beer factories through many different cultures through history have existed for thousands upon thousands of years. It would figure beer would give us good mathematics at some point or another. So, my goodness, my Guinness, we get a tea table. And we can talk about a population just from our sample data. And we can talk about how well our sample data tells us about that population, because we can have confidence levels in it. Again, the overall caveat is that when we go out and measure things, we are random in our measurements. And so here we take that value, the critical value of 2.145, and it looks like this on the T table. And we have 95% of our stuff. 95% of our stuff is in the blue area, and 5% is on either side, or 2.5% in the tails. And so we want to be 95% confidence. We need a critical value of 2.145. And so that's going to let us develop a margin of error. And the margin of error develops out exactly like it did in the Z-scores. Or Z-table. So our margin of error, the error that we have, is going to be what the critical value is times the sample standard deviation, because it's the only thing we can measure, divided by the square root n. Now for the people using their calculators, you get two standard deviations. One of them has the x in it and the other one has the s in it on the TI-80s. The TI-84s writes the sigma and the s. You will want to use the sample one. Well, how do we tell the sample one apart when the calculator spits out the two values? And so what I want to do here is when you get the two values, the sample one is always slightly larger. Right? And that has to do with when we're doing the standard deviation. Let me just really quickly get the x minus mu squared over big N, everything under the square root. And s is x bar minus mu squared over n minus 1. Well, I'm dividing by a slightly smaller thing. Right? So 15 divided by 3 is 5. It's a larger number. But then 15 divided by 5, which is 3. So when I divide by a small number, I get a bigger part. This number is slightly larger than this one. Slightly larger. So this one should be the smaller one. So when you look at your calculator and you get those two standard deviations, one is going to be slightly bigger than the other. The bigger one is your sample. It's the best way I can think about explaining that. You'll be seeing these two things. You have to remember them. You look at your calculator. Some calculators have them labeled as an S and an X. Some have them as a sigma and an S. So on the TI-84, it does the sigma X as the population one, and it does the capital SX as the sample one, and the sample is slightly larger. Let me look at my TI-30. My camera still hasn't come. I actually just requested a refund from Amazon because it hasn't shipped from the place in California. So I don't know if I'll be doing good calculator. I'm going to try if I won't find a way to use my phone to do calculator demos. I don't have that right now, but I will see about that. Let's see here. Okay, I've entered some data. Calc. So yes, on the TI-30, the sample standard deviation has a capital S, and the population also has a sigma. So they added the sigma from it. That's the 30XIIS. I don't remember the other 30s. So that's the best I can give you with the calculator here, is when we're doing this, look at your calculators. They will have an S or a sigma for the standard deviation that you want. We are using S. But if you ever are unsure, when we don't know as much, right? And there's kind of a philosophy under this. Our standard deviations are wider. When we don't know as much, our confidence intervals are wider. These things get bigger the less information we have. Our spreads get larger. And that should kind of tell us of what's going on here and how this actually ends up being a good thing for us. All right, so our error is what our critical value is times our sample standard deviation divided by the square root of the number of samples we have. And so we can construct confidence intervals out of these. So let me get over here. Let me scroll down, clear some space here, and we'll look at a confidence interval for the t-table. Oh yeah, the book does have a picture of Bill Gossett in there. All right, that's not too bad. Interesting character. He was definitely a mathematician of some. All right, I'm trying to get here 2 seconds here to pull up the problem. So we want to find a confidence interval from the standard deviation. Well, let's yeah, I'm going to do the coffee shop problem, but I'm going to walk through what they ask us to do first, and then we'll go to the coffee shop problem and see what happens with it. So let me get back to the slides here. All right, so here are some nice steps that we can do when we have to work on these things. So, well, first thing we have to know is, do we not know the population standard deviation? Verify that. And verify that the sample is random, that we're grabbing our data randomly. Those are the two things we need. Now we want to know that we are trying to read this slide and say it right. What you want to know is we don't know the population standard deviation, and we actually don't know anything else about it. These are all the things that we don't know. Verify that the sigma is not known, and that we have 30 or less, and that we are approximately distributed. I'm trying to think of it. It's like the opposite of the central limit theorem, right? Right. The central limit theorem says, hey, we know these things, and we have 30. Well, here we're gonna deal with the other end of it. We're gonna deal with things where the central limit theorem is out, and so we can't use the central limit theorem in a normal distribution. So I would rewrite all this as saying not the central limit theorem, right? This is the opposite of the central limit theorem. So we find the sample statistics. We find the number that we have, the average from the sample, and the standard deviation of the sample. Right? We plug them into our calculators. We get our n, our x bar, and our s, which spits out of our calculator calculations. Right? Then we want to figure out what the degrees of freedom are. And the degrees of freedom and the confidence level. We do all of that to look up our critical values. Now the degrees of freedom are nice. It's one less than what the number of samples we have. And we use that table to pull it out when we know our confidence level. And that will give us our critical value TC. Now remember, there's also a negative TC, negative critical value. It's a two-tailed thing. So whatever the one value is, we get the negative version of it also, which is why this talks about the left and the right endpoints, right? Of course, your book is writing it like this. I tend to write it as x plus or minus e, right? The book will write this out as two things. It'll say x plus e is your left endpoint, x minus e is your right endpoint, and then you get that the population is somewhere in the middle of these. That's how the book wants to write it. I think writing these two things is an extra step when you have a symbol that says, hey, I can do two things. Like walk and chew gum. No. Coming through. So these are the steps that we need to do this. This really is the same steps that we did for finding a confidence interval with the z-score. We are just using a different table. And we are using the sample standard deviation, not the population. So let's look at a problem here. So you randomly select 16 coffee shops and measure the temperature of coffee sold at each. I'm thinking of a lawsuit that this is referencing. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold, assuming the temperatures are approximately normally distributed. So it's assuming that your sample or population error is random enough that you would be looking at a normal on this. Sorry, I'm thinking of that McDonald's lawsuit and what was their coffee temperature. I think 185 degrees because it gave the illusion that it was fresh if it came out steaming, which is enough to cause scalding. Well, this is probably a safer temperature, but I digress. All right, so let's try to solve this problem. So we have 16 coffee shops, so that's our N. We have a mean in our sample, so X bar is 162, and our S is 10. Our C is going to be 0.95. So let's put that all together here. And since this is coffee and I'm thinking hot, I'm going to go orange. So 16 coffee shops were surveyed. We found that the average of our samples was 162 degrees Fahrenheit. Our standard deviation of our samples was 10 degrees Fahrenheit. Get my degree symbol in there. And we want to figure out with a 95% confidence. Is it 95? Yes, a 95% confidence what we can say about the population. So I want to focus here. We randomly selected 16 objects, right? So randomly selected. It's a fair assumption that coffee is made to a similar temperature, so this should be normally distributed. Our experiment found an average of 162.0 for our surveys. Our experimental standard deviation was 10 degrees. And we want to talk about every coffee shop. Right? So we want to be able to talk about what the average value would be for any coffee shop. Now I'm going to write this as the average value. A good estimate for the average is the average of our samples plus or minus whatever error range we have. So I have the 162 here. I need to find E. And E, our error, is our critical value times our sample standard deviation divided by the square root of N. So I have to find TC, my critical value. To do that, I need to know my degrees of freedom, which is N minus 1 or 15. So I'm going to flip over to my chart. And I want a 95% confidence level with 15 degrees of freedom. So I am getting a 2.131, right? 95% confidence, 15 degrees of freedom, 2.131. So TC is equal to 2.131. So my error is 2.131 times 10 degrees, Fahrenheit divided by the square root of 16. So I plug all of this into a calculator. And I plug all of this into a calculator. There, we grabbed it out. So 2.131 times 10 divided by the square root of 16, which is going to be 4. And I get 5.3275 or 5.3. Now here's something that the book doesn't state, but in every experimental science book I've had. If your measurements are to 1 decimal place, you never let your error have anything more or less than 1 decimal place. If your experiments are to the ones digit, your error is to the ones digit. Whatever your experimental number of precision is, number of decimal places, that's how you're going to report your error. So that 5.2375, or what was it? What was my answer? 5.3275, so it's going to round down to 5.3. So I can say that I have 162.0 plus or minus 5.3 degrees Fahrenheit. All right, so what does that end up meaning? That means that the lowest value that would be within 95% confidence, or 95% of the things we should see, the lowest value is 162 minus 5.3, or 156.7. And the highest value would be 162.0 plus 5.3. And so that's the range of values that we are 95% confident that represent the population or the average temperature of coffee. If you were to go into a coffee shop and come through. And notice, we can now have a 95% confidence about a true value of our population based only off of samples. Nowhere did we need to know anything about the population other than it's most likely normally distributed. And to be honest, unless something is screaming that there's a systematic in it that makes it not normally distributed, most things are normally distributed. If there's one true value that they're centering on, the error tends to throw it both positive and negative in a way that makes it normally distributed. The only reason that wouldn't happen is if the error is always positive, or the error is always negative, or if positive values multiply more than less. And that's actually very rare in reality. And so normal distributions, and why I said chapter 5, you got chapter 5 down, you've got most of your statistics, is because reality and randomness and error tends to be fair, right? I mess up in the positive just as much as I mess up in the negative. And if I plot that all out, I get a normal distribution. So the criteria we need here is, if I'm going out measuring coffee shops, their temperatures tend to be plus or minus some truth value. And that truth value is the average. And the error, or the spread, takes into all the factors of why they might be bigger or lesser than that. And now if I were to go to a coffee shop, I would be 95% sure that my temperature would be in between these two numbers. And so that's what the t-distribution lets us do. And that's how the t-distribution drives us through all of this. And again, my goodness. All right. Let's look at another sample here. Let me see if I can get it up here. erase my blackboard, which in this software is scroll down. I think I'll change to neon pink or purple. And we'll come over here. All right, I think this is, yeah, this will be the last one we look at here. And this will get us through confidence intervals with our t-tables, and then we'll look at some decisions we can make. So you randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. The sample mean is 9.75 days, with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days the car model sits on the dealership lot. This is actually a really important calculation, having these values for car dealership lots and having them up, because car manufacturers don't have huge places to store their cars. This is something that the modern world logistically has kind of fallen into, and actually in this time period where consumption rules are changing a bit, some of this mentality is being stressed, and so we kind of have to look at what happens here. I noticed when Walmart started going online that Walmart stores in odd areas stocked things they didn't sell because the stores became part of the warehouse system. And so what you would try to do is you would try to push things out as far away as you come from the factory, so or your main distribution warehouse, so you didn't have to have a large storage space. And so you push things out. And so, you know, Walmart puts things into their store shelves as a place of storing it, and then they need to sit in the background and figure out how quickly a store sells before they order a new product through the warehouse. And so there's a flow of how fast things need to go out so that you never fill up any of the spaces so that it's overflowed. And car dealerships are like one of the first places this just-in-time model came through, because storing a large quantity of cars was hard. And that's why like a bad run of cars can be really devastating. I've seen documentaries on like lots of a particular model that didn't sell, like the Edsel, and how they have to funnel them out to places like the aircraft graveyard in the Midwest, where we retire all the planes but kind of sit them there as parts or decommissioned. Same thing happened when cars didn't sell. They wouldn't be moving off the dealers' lots, but they're coming out of the factory, and you can't gear down the factory really quickly. And so this calculation here is actually really important. And again, my goodness, a beer calculation gets it, that we have an idea of how quickly things are going to flow off of a car lot so that the factory is producing enough to meet demand, but never have to build a storage warehouse. And this is part of what's called the just-in-time model that we've been using for modern distribution for a while. And it actually bears reflecting in modern circumstances. The just-in-time model can be stressed by a change in flow rates of consumer goods. And right now we're living in a time where flow rates are changing. So think about this when we look at this car problem, that it's not just a problem in a textbook, right? I mean, the numbers are broken down so we can use this. But in the actual application of this in industry, this becomes important because the manufacturer for that dealership would have these numbers for every dealership that it has to deal with. And those numbers would turn into how many cars they need to have within certain time intervals. And as long as they can be coming out of the factory or off of the ship at that rate, the car dealership will never have an empty space. And if they're not producing too quickly, it won't back up, and they have to find a place to store them. All right, so let's look at what we can get out of this. So we have randomly selected 36 cars. So we have our value of n being 36. Our sample mean is 9.75, so S is 9.75. or I'm sorry, the mean is 9.75. S, the standard deviation, S, is 2.39. So X bar is 9.75, S is 2.39, and our C is 0.99. So let's get all of this down here. So let's come, whoops, here we go. So we have 36 samples. I have a mean of 9.75 and a sample standard deviation of 2.39. I'm going to change the height of my tablet. My hand is not quite right yet. Okay, so that, and our confidence, so we want to be almost 100% sure. Okay. We want a 99% confidence in this because we have no room for large errors in this. Right? Backing up cars and car storage will be large. So the first thing I'm going to calculate here is, hey, I know I need my TC. So my degree of freedom is n minus 1 or 35. So we're going to go back to our t-table. So we go back to our t-table and we are looking at the last column because that's the 99%. We're looking for 35. And that has a 2.724. 2.724. So our critical value TC is 2.724. All right. So our error is 2.724 times our sample standard deviation divided by the square root of n. All right, let me write the equation over here instead of scrolling back up. It's TCS over square root of n. All right, I've measured to 2 decimal places. So I will want my error to be to 2 decimal places. So 2.724 times 2.39, let's see here, 2.724 times 2.39 divided by square root of 36. And I get 1.08506. And so for 2 decimal places, that's approximately 1.09. Well, that means that the population average is our sample mean plus or minus our error. And our endpoints then would be, I'll do the subtraction first, so 9.75, because this tells me I'm doing 2 operations. One is addition, one is subtraction. So 8.66 is the smallest value we would expect to see. And the largest value we would expect to see is the addition, 9.75 plus 1.09, which is 10.84. And so if we want to be 99% sure that we can have a car sitting on a lot, that's the amount of time. And if we know how many cars that lot can have, plus this time limit, we can start building a model of how quickly our production needs to meet our just-in-time distribution coming across. And so this is a t-table. It does nothing different than we did with z-scores and our normal distributions. We just are working from a place where we don't know about the population, and it lets us infer about the population within the confidence. It's wider in the tails. There's the error of the unknown is accounted for. And what determines that level of error we unknown is the degrees of freedom, or how many samples we have. Every additional sample that we get gives us one more piece of information about the true value. So the more samples, the quicker the t-table approaches the standard normal of the population. And so this nice little chart at the end here, and this is the last thing I'm going to share on this, which I like this slide. And it says, am I using a normal or am I using a t? So first thing, is the population normally distributed, or is n greater than equal to 30? So is the population normally distributed? No. Is n greater than equal to 30? No. Well, we're out of luck. We don't have a tool for those yet. All right, remember, we're dealing with things where the error normally distributes. We'll look at things that are skewed shortly. All right, let's say it's yes, the population is normally distributed, or we have more than 30 results. This is why I say take more than 30. Right? If I ever have someone in a lab, try to get 30 things. So is the standard deviation of the population known? Yes. Use the standard normal table. Do you know it? No. Use the t-table. And that lets us find our error, and that lets us talk about the confidence of what we know about the truth. All right, so this has taken us up through section 6.2 in the book. I will get the homework updated, and I will put some more examples online of different problems out of the textbook. If you have any questions, email them to me from Pearson. I will do example videos, and I will be setting the exam schedules for the next part of material. We have one more exam, and then we have one project that loops its way final. You'll be having all of that. I have almost every piece of material to get us all the way out through the end of the course. I'm going to make this announcement here, and I'll put it in my email. If you're not graduating or transferring this semester, if you plan on coming back next semester, realize that because of this change in education, I can give you an incomplete all the way up and through next fall, and we can work on completing the work that you need to finish the grading. So if you have any time constraints, let me know. Email me, talk to me, and we can work out what's best. If you are looking to transfer and you're looking to graduate at the end of the spring semester, we need to try to wrap everything up by May 13th, which is the date that the grades need to be submitted. And so if you're trying to do that, also let me know so that we can organize these things and make it work for you. Right now I'm putting together a schedule and I'm doing it, and I'm like, hey, let's make this work. But if things aren't working, you need to tell me. Otherwise, hey, no one's complaining. Let's keep on moving. All right, my goodness, my Guinness. I love t-distributions just for talking about those crazy posters. And who knows, maybe I'll try to put up a my goodness poster if I can find one. Be safe, be well, all right? I hope to see you all in person soon. And I wish you well until then.